All right, we're going to get settled in and get this panel started. So we had a great panel yesterday on what we called the new spectrum pipeline in light of the One Big Beautiful Act, or the HR1. But for some context, just keep in mind that the total amount of spectrum that we're talking about that has been allocated in the United States to cellular systems, even with this 800 megahertz of spectrum that we talked about yesterday, and Wi-Fi systems, it's on the order of 2 gigahertz of spectrum, okay? There's a proceeding at the FCC called Satellite Spectrum Abundance, and they're looking at 20 gigahertz of spectrum. That's a factor of 10 more spectrum that's on the table and being explored. And that's exactly why we wanted to put a panel together with this set of panelists and with our moderator, Veena Rawat. So I'll introduce Veena. She's a member of the SpectrumX External Advisory Board. She spent many years running the rough equivalent of the NTIA Institute for Telecommunication Sciences here in the US, in Canada. It's called the CRC. She's now a consultant and works a lot. She's had a lot of experience at the ITU level. And so we're really grateful that she stepped in to moderate this panel. And we're looking forward to this conversation. The other thing is, because it's so much spectrum, there's a lot of in-band and adjacent band issues with other uses of spectrum, and particularly some scientific uses of spectrum. So we wanted to expose that in today's conversation. With that, I'll hand it off to you, Veena, and feel free to run with the panelists. Thank you all very much.
Thank you very much, Nick. And yeah, I ran Communications Research Center for a while, but I also was the Canadian regulator. And sometimes when in the Zoom calls, you see me as Zoom, in the participant's name as my name with GSMA, because they are my main client for my daytime consulting. But at the same time, you also see sometimes Zoom Canada. And that is only because I participate in the ITU meetings where, you know, I participate as a Canadian delegation because I did that for decades. So that's the other thing I guess some of the people may know me for, and I'm proud to say that WRC, this whole discussion about especially using the higher frequencies, terahertz frequencies by passive services, it started in 2000, but the conference I chaired, the WRC 2003, there were a few resolutions and decisions came out for terahertz frequencies at that time. So the bands covered in the satellite abundance spectrum, go way back, but now they have, with the recent FCC notice, it's wonderful to be able to talk about them, especially for commercial services. We have a wonderful panel here, and we start looking at the panel in the order I'm looking at. Starting with Beau Backus, who represents NOAA plus few other organizations, and Beau will mention it to you. We have Pree, and he represents the NRAO, the radio astronomy interests. Then we have Luca Lodigiani, I hope I'm saying that right, who stepped in only yesterday, later than less than 24 hours. So really, really good, brave Luca, and a special thanks to you, because Brian had to go for some important commitment. And last but not least, my friend Jennifer Manner, who has just years of experience with the government and the private sector. So very happy to see every one of you on the panel. And I had not mentioned, but I thought when I looked at the document, I just found it very complex, comprehensive, tons of questions and everything else. So I thought maybe I will just take 5 minutes or 6 minutes to just set the context, and then you correct me if my context is not right. So I thought I'll just start with this and to give you some of the context. I have to say that I'm very, very pleased with this FCC's initiative, very forward-looking, and something which SpectrumX can engage as much as possible, because it is a little bit longer-term looking. But every time I talk about SpectrumX engagement in some of the ITU topics, well, the answer is always because it's very short-term. We need to respond to WRC 27, or even WRC 31 may not be, long enough. So So it's really good that we have this initiative, and this initiative is satellite initiative is not just in the U.S. There are many other countries with their space aspirations, etc., are looking at the spectrum for satellite services. And last but not least, I should also comment that even the WRC 27 agenda, I don't want to forget that, is 70%, if not more, is really looking at the satellite issues. So the importance of the satellite services, the role they're playing for all sectors, consumer, enterprise, public sector, defense, etc., is well recognized, is increasing, and hence the interest in finding more spectrum for the satellite. Okay, so next slide. I'm just going to thinking that there are students in the audience, and just tell them a little bit about how the allocations work and what the bands are here. The panelists know all this. So very quickly, just going over this, and let me know. I don't want to go more than 4 or 5 minutes. Just highlighting the bands, the two categories of bands. The discussion in 12.75 and 42 gig has been going on. I don't know if it's a decade or not, but it's been going on. And particularly some of the issues are whether we do the satellite services in 42 gig, and it was also part of the UMFS, the mobile fixed flexible use by FCC. So that's why it's called further NPRM, because FCC has taken some, has made proposals in the past. And then this brand new NPRM, which is really looking at 50 gigs and above, looking at the spectrum in this range, 51.4, 52.4, and parts of 92 to 114.25. And I will show you, this is really some daring proposals from my perspective, in the sense that this range, the last one, the W band, if you go, so let me just finish here. The W band, in this range, I did not find FSS allocations. So, a lot of other allocations of commercial services, and of course, scientific services, radio astronomy, and other passive services. So to come in and say we are going to be putting a commercial service in parts of this range is a very good initiative to learn from and see how a lot of issues could be addressed. So moving on. So I wanted to just give a flavor of how the allocation table of FCC looks like, especially for any students in the audience. And as here you can see, the table is international table on the left side, and ITU thinks in terms of region 1, 2, 3. If you don't see the bars, the vertical columns going through all the way down in the international table, that means those are global allocations. So here it says fixed satellite, fixed mobile, they are all globally allocated. And then United States adopts what it needs, what it suits, what would suit its needs in their own table. And they divide the table into the federal use and the non-federal table, as we are very well, most of you are aware of the NTIA and the FCC use. And the last column just talks about the specific FCC rules. I'll just run through these bands just to show that most of these allocations, let me comment band by band. So here we have the fixed satellite already, and there are issues which FCC is looking at to really say, should we remove some of the restrictions so that the band could be used more freely for fixed satellite services, in particular for the uplink. Okay, next one. Next slide is 42 to 42.5 gig. This was under major discussion under WRC 19 when we were looking at the millimeter wave spectrum for 5G. And there is, there are decisions made from WRC 19 for the millimeter wave spectrum. There is a debate out there to what extent since 2019 that has been materialized, but I'm not going to go there. But basically, that was the debate. So that a number of proposals have been made. But this is in a globally identified fixed satellite service band. So it's a beautiful band for fixed satellite services. Moving on. So those were the NPRM bands. 51.4 this gigahertz. This band has been on the books for a while, has the global fixed satellite service uplink. It pairs with the, somewhere in the 40 gig, 40 to 50 gig range with the downlinks there, including the 42 gig, probably will be, paired with. And again, it's also considered for gateways and feeder links now as we speak. So I don't think there would be major technological issues, etc., because the development is happening in the FSS in there. Next band is parts of the W band. If we go, Emily, in the next slide, the W band is, FCC has noted, if you look at their NPRM, from 92 to 114 gigahertz, and parts of their these bands are to be identified for fixed satellite service. And you will see, if you look at the allocation tables, that bunch of these bands, and you will hear to the panelists, are for scientific services, whether they are within these bands FCC is considering or adjacent to it. And that would be the biggest challenge I think we will be debating today, is how the coexistence will happen, or how the out-of-band unwanted emissions will protect some of these passive services, and the extent the passive services are already looking at this. And when I say passive services, I mean radio astronomy, Earth exploration, passive, and other space research, etc., passive services. And today, I think on panel, we have really good people here to talk about these services, Chris and Beau. So we should make use of it and see where the SpectrumX could, engage, particularly in this band. I may have just one more slide, and that's, I will go to, I'm not going to go to these, so I will just continue. I'm just showing the allocations for W band, but the last slide, if I can get to Emily, these are examples of how the footnotes are given. Yeah, so that's the last slide. And basically, we can't talk about spectrum without talking about the ITU and the WRCs. And all this to say that while the initiative FCC is taking is not on the WRC 27 or on the WRC 31 plenary agenda, these bands are on the W band, parts of the W band are already on the agenda for WRC 27. And if you look at the agenda 1.18, and Chris probably can a lot more, protection of radio astronomy in bands above 76 gig. So the limit is, there's no limit here. You go from above 76 gig, and wherever you have radio astronomy, how do we protect them? And it's very broad. Active services, which could be terrestrial, which could be, satellite, mobile satellite, fixed satellite services, etc. So it's a very broad agenda item, and that agenda item is being addressed now as we speak through the ITR studies. And then WRC 31. So the WRC 31 has the agenda for, it's a preliminary agenda, can change significantly. Agenda, this item is looking at terahertz frequencies for 6G. And I just noted highlighted the overlapping band with the FCC NPRM. So I'm just asking myself the question going forward, depending on the timing of the FCC decisions from this docket, would there be, some agenda for WRC 31 proposing the more commercial satellite services in the bands which FCC is considering above 42 gig? I think I would look at most likely in the W band. Okay, so that's kind of my context. I hope the experts will elaborate more on the NPRM in terms of what their interests are, whether they commented on it, whether they got challenged on their comments, etc. So I thought we would start with Beau, because Beau has it's all background information in mine, Emily. So I can stop here. I would like to start with Beau, because Beau has another much more detailed context for this NPRM, and I saw that after I had prepared my slides. But anyway, we can start with Beau, and I'll let Beau say a little bit more about himself, and also talk about the satellite spectrum abundance from remote sensing and from weather prediction applications, etc. Take it away, Beau. Ten minutes. I may have violated myself. It doesn't matter.
Well, thank you very much, Veena. I immediately fumbled my mouse and I couldn't find my pointer, and suddenly there was that terrible silence. Thank you very much. I think for what, and if we go to the next slide, I'll just say that I'm with the Johns Hopkins Applied Physics Lab. A lot of my work involves both supporting and assisting NOAA in its spectrum management work, specifically the satellite side, as well as and very predominantly in this presentation is with the Geoscience and Remote Sensing Society with and I chair the Frequency Allocation and Remote Sensing Technical Committee, and very much concerned with ensuring passive band protection, because it's such a critical role for Earth exploration satellite service. So let's start off with a little bit about the satellite spectrum abundance proceeding, FCC 2529. I won't spend any real time on the first couple bullets in that Veena has already described these to you and what frequencies we're talking about. My focus and concern is primarily in the 50 gigahertz and the W band arena, and the importance that plays in meteorological satellites and such. But I did want to point out one other very important point here, and that is this third bullet, which is the FCC stated rationale, which is U.S. leadership in the global space economy. I believe Brendan Carr, the chairman, the FCC, sees that this is a critical part of both economic and national security for the spectrum, and their explicit goal is to provide American companies with abundant spectrum to outcompete global rivals in the race to deploy next generation satellite networks. So want to also point out that this sector, the space sector, is rapidly growing, and estimates have numbers in the $1.8 trillion over the next 5-10 years in terms of space industry. So a very important role. Next slide, please. And in that role, there is already throughout the RF spectrum, there are users for a variety of different purposes, and some of those purposes have an importance that's not typically realized in the public's eye. The first thing here is just to talk a little bit about, well, what is passive sensing, and why is the Earth exploration satellite service uniquely vulnerable to radio frequency interference? Passive remote sensing, as it says, is passive. It's just the receiver in space, but it's fundamentally different than active communications. You don't you really have to look at it a little bit differently than your normal link equation. EESS instruments operate, they're really highly sensitive receivers or radiometers, and they measure naturally occurring electromagnetic emissions. I mean, we emit energy from the Earth's surface and the atmosphere. Everything here emits these signals, but they're very, very weak. And so the noise floor, it's much, much weaker than the typical noise floor for a communication system. And in that is critical data that we glean from absorption. Certain frequencies have different absorption characteristics. It's all based around physics as to where these passive bands are located. And we use those in order to determine how much water vapor there is, what the soil moisture is, sea surface temperature, and so forth. So it plays a critical role in society. With interference, we actually could start to see basically what you could call loss of data. We could actually, if it's extremely weak energy, we might not be harmed much by it. But as that, if it's really strong energy, that's interfering. And I'm talking about the difference between natural transmissions and man-made, or as I say, anthropogenic energy. And that is where we run into the problem. When you add in anthropogenic energy into the natural energy, it accumulates, it adds, and it becomes greater. But we don't know that there's this non-natural energy there. Our systems can't tell the difference at this point. So we're potentially seeing insidious type of interference occurring where we think we have a measurement, but it's not really a true measurement. Some of the bands that are important for weather prediction and climate modeling include these here around 23.8, 36.5 gigahertz. The W band for that. And I'll mention that the 50 gigahertz is extremely important to passive band remote sensing. And then one other one that we have to watch for is harmonics that can occur and also further degrade, even though they're not directly adjacent, but the radio frequency harmonics could actually also put energy into a passive band. So next slide, please. Looking at some of the emissions, the threat basically that we look at, and I really don't want to call it, I mean, I know I have it listed here as the threat matrix, but truly it's where our concerns are. And so it's the potential for having these degradations that I just described. Out of band emissions, transmitters aren't perfect. They can put energy in areas where they shouldn't, and it can become a source of interference. Aggregate interference, it's a cumulative effect for thousands of satellites, tens of thousands, maybe even more, probably a lot more. I think in some ways, instead of calling it the satellite spectrum abundance, just call it satellite abundance. We will have lots and lots of satellites. And then finally, many of these, in fact, the vast majority of the satellites we're talking about, these mega constellations, are not in geosynchronous orbit. They are the non-geosynchronous orbit system, which means that they move across the sensor's field of view and making it that much more challenging to determine where interference could be occurring. And it is a real challenge. Next slide, please. So looking at this from the contested spectrum landscape, just kind of, I'm just going to step through here really quickly on looking at the various stakeholders' positions. There's a scientific and related coalition, government coalition, consisting of people like the IEEE's GRSS FARS, as I mentioned earlier, Committee on Radio Frequencies with the National Academy of Sciences. The National Oceanographic and Atmospheric Administration has their concerns because of this could potentially affect their forecasting. And so basically, they have been looking at this in terms of it's very important to the scientific community that we don't have insidious contamination or degradation and so forth. Additionally, looking at it kind of from what I call international dimension is the Coordination Group for Meteorological Satellites and other similar ones. This CGMS, it's a multilateral organization of various global meteorological satellite operators, and that includes NOAA, EUMETSAT, the Japanese Meteorological Agency, and so forth, who are all members of CGMS. And the reason why this is of concern is this is a U.S. issue, but it actually has global implications, since the regulatory action by the U.S. Can lead to interference in critical bands that will actually potentially impact or degrade U.S. data, but it will also potentially compromise the integrity of the global observing system. We trade data. All of these different agencies shared information on global on global meteorological effects. The next one is the commercial push for growth, satellite industry and think tanks, and that is the commercial industry, the commercial satellite industry, and their associated policy organizations are advocating for, to modernize the spectrum rules and facilitate much faster growth than right now is possible. Among other things, you look at the cycle at the ITU, it's 4 years. It can take you 8 years to basically get through something that needs to change. And there's a lot of work that goes into it. And then finally, I just mentioned the Federal Spectrum Manager, which is NTIA, and the role that they have, which is managing the federal government's use of spectrum. And they serve as sort of the primary advisor to the executive branch on telecommunications policy. And I make a note here that the NTIA is also located within the Department of Commerce. And so in many ways, they have a challenge in both looking towards improving the commerce health of the country and so forth, as well as also looking at, and sometimes it becomes a conflict with what the federal government's needs are for spectrum use. Next slide, please. So just kind of break it into kind of the EPFD limits, which is viewed by a lot of folks, especially in the commercial sector, as being an outdated regulation, and by others as being essential protection. And that's kind of the question. You can see here is industry's argument that the current limits that are in place are actually old and not needed. They were developed to protect just the geosynchronous networks and so forth, and that maybe there is a better way to do this. The scientific community views that these EPFD limits are very important. They're critical towards the design of their sensors. Eliminating this protection could expose radio services to chaotic and unpredictable interference environments, and design becomes, for future systems, so forth, this also becomes very difficult to establish. So I won't go through all of the different points, but basically, there's a philosophical divide here. Industry sees the EPFD as a barrier to maximizing their capacity as they increase their numbers tremendously to meet user demands. And the scientific community basically sees these limits as an essential tool for managing aggregate noise. Next slide, please. So kind of stepping through a couple of proposed mitigation strategies. Have the site-specific versus blanket protections, which is a clear distinction between site-specific protections with blanket rules. NTIA and CORF support coordination zones and geofencing to protect high-value fixed assets like the Goldstone Deep Space Network, or the Green Bank Telescope just out here to our west. Well, I can't say for where it is, but at least my west. And am I over time?
Yeah. So, but you have a very nice slide for the engagement at the end. So I'm wondering whether you can bring that.
I will. Let's go ahead and go back.
Yeah. And then anything you haven't presented, we can bring it back depending on the time and the questions.
Very good.
Certainly, very good information here.
So I won't read through this. Just
No.
know that you have static versus dynamic protections and site-specific versus blanket protections. Those are ways forward, or they could be, depending on how we work this. Next slide, please. And I just want to say here, we've got a variety of challenges and strategic gaps that we need to work through. And we could spend way too much time on this. So next slide, please. And then looking here, some strategic opportunities that SpectrumX can consider. Basically looking at advanced aggregate RFI modeling for NGSO systems, RFI measurement characterizations, and dynamic spectrum sharing for scientific protection. Basically, some really good possible opportunities here for SpectrumX. And I believe there's one more slide here, and basically get into some of these key technical questions that I think, and I think this is what you were talking about, Veena, for the,
Yes.
yeah. This is basically looking towards, where should we be, and specifically SpectrumX, answering some of these critical questions. And you can see these here. I don't need to read them to you. But these are just some of the unresolved questions, I think, that will help with starting to get towards an understanding between having to decide on something that's has very strong, clear numbers. Basically, when you start talking about the economics of spectrum need, those are clear numbers. But when you start talking about the scientific needs and needs for meteorological, which is safety of life, safety of property, and so forth, that's harder to put a serious and clear number on it. And it's very difficult on trying to being able to make decisions, especially when you're a regulator, spectrum regulator, on how you balance between one and the other. And these questions basically push towards what can we do to start getting to a common denominator. Thank you.
Thank you very much. It's great, and I think we could bring up a couple of your slides in terms of questions during the Q&A period as needed. But certainly, you make a case about the use of some of these band by passive services and the need for protection, and how do you protect even in adjacent bands is a challenge. Next, we go to Chris, and Chris will express his views about the how do you avoid the interference from all these non-GSO constellations we have been talking, Beau mentioned. And take it away, Chris.
Thanks, Veena, and thanks, Beau. Obviously, we have a lot of similar concerns, although often complementary in terms of the direction that we're concerned about, space to ground versus ground to space, of course. My name is Chris Pree. I'm the Assistant Director for Spectrum Management at NRAO, and I've been with NRAO for the past 4 years. Before that, I was a professor of physics and astronomy at Agnes Scott College. Next slide, please. So just to start with, since I'm not sure everyone is familiar with NRAO, we are an FFRDC, part of the National Science Foundation, and we have a mission statement that says what we do. We provide world-leading telescopes, data, instrumentation, and expertise. We train scientists and engineers, and we promote astronomy to foster a more scientifically literate society. And as Beau very rightly pointed out, in the face of clear economic advantages for economic competition in terms of spectrum use, those are less easy to make, although I think as an educator and as a scientist, that some of the most amazing things we do as human beings are advancing our understanding of the universe, and radio astronomy has certainly played a large role in that. Next slide, please. So to start with, I just want to tell you about, very briefly, the telescopes that the National Radio Astronomy Observatory operates. One you may be familiar with. There's actually a new series by the guy who did Breaking Bad that starts set out at the Very Large Array. I think it's called Pluribus. That starts, so it's often been used as a scene for movies. You're probably very familiar with it. It's out in the plains of St. Augustine. And I just wanted to point out that it has continuous frequency coverage from 1 to 50 gigahertz. And what we call Q-band covers from 40 to 50 gigahertz. It's a 10 gigahertz receiver, cryogenically cooled, extraordinarily sensitive to the type of space-to-ground transmissions that are being considered here by the FCC. The VLA also functions all the way down at 1.4 gigahertz, which, as Beau very rightly pointed out, the physics are immutable. We can only observe the neutral line of hydrogen, H1, at 1.4 gigahertz, and we can't observe it anywhere else. And so if we lose that part of L-band, that is a great loss to our understanding of the universe. Next slide, please. The Very Long Baseline Array is also operated by NRAO. It covers half the globe, practically from Hawaii all the way up to St. Croix, with 10 antennas. They are similar in size and construction to the VLA antennas, but it was dedicated as an interferometric array afterwards. It has even greater frequency coverage. It starts down at 312 megahertz and goes all the way up to 90 gigahertz. So its surface is more accurate. It can operate up to 3 millimeters. And its Q-band is rated from 41 to 45 gigahertz, again, overlapping the one of those bands under consideration. Next slide, please. The Atacama Large Millimeter Array is operating in Chile. You may have seen images of this fantastic telescope. It actually operates up to from 35 gigahertz up to 950 gigahertz. It is in an extraordinarily unique location on the surface of the Earth, very low moisture, very low precipitation, and so it can operate for most of the year and operate at those very high frequencies where, of course, water vapor is an issue, lots of other places on the surface of the Earth. Again, what gets in the way of our faint signals is the bread and butter of Beau's observations of that water vapor. So again, complementary concerns in some cases. But I want to point out that band 1 of ALMA operates from 35 to 50 gigahertz. So there's a 15 gigahertz swath there. And you may have noticed that some of these bands that radio astronomy operates in are extremely optimistic because, of course, the amount of spectrum that is actually primary for radio astronomy below 100 gigahertz is quite small. It's on the order of a few percent. But radio astronomy has built broad bandwidth observers to help us to make our observations as quickly as possible to increase our signal to noise. Next slide, please. And the Green Bank telescope was mentioned by Beau. That image up in the right shows the red rectangle indicating the 13,000 square miles of the National Radio Quiet Zone. We are the star on the left. That is where the Robert Byrd Green Bank telescope sits. It is the world's largest fully steerable radio telescope. It is 105 meters in diameter. It's an incredible feat of engineering, and it's been operating since about the year 2000. To the right is the Sugar Grove Research Station, which is a NSA facility, and we are both protected. Both the Sugar Grove and Green Bank are protected by the existence of the NRQZ. Next slide, please. Oh, sorry. If you go back, the operating range of the GBT goes from 290 megahertz up to 100 gigahertz. And its Q-band receiver goes from about 40 to about 50 gigahertz. Next slide. So I think this will go sort of step by step. If we can go back one step, Emily. So you imagine a radio telescope, and what happens with radio telescopes is we put them out in remote sites. And next tab. We try to protect them in the origins from things like cell phone towers, transmitters that are fixed transmitters located on the surface of the Earth. And mountains, other topological features can provide propagation protection against those transmitters. Next slide. Or next, yeah. So we build interferometers far away as we can. Next, please. We establish quiet zones and dynamic zones to try to control the types of transmitters that are located close to our telescopes. Next tab. And then satellites appear. So we have constellations which are now broadcasting from space to ground. Next slide. And of course, all of these various components are now communicating with one another. We have space to ground, ground to space, and indicating space to individual user, right? So we have actual handset, which is extraordinarily complex to coordinate. If you want to look at the aggregate effect of satellites to a fixed transmitter, it's a lot easier than to a whole host of mobile receivers. Next slide. So the challenge is that, well, first of all, it's a little bit different for radio and optical telescopes. I am not an optical astronomer, and I know that the challenges for satellite-borne transmitters are huge, especially as those frameworks get large. But the old reality for radio telescopes is that we put telescopes in remote locations, and that often protected us because we looked at the sky and the sources of RFI were located on the horizon. But the new reality, of course, is that we have things above us. And so where our main gain is, right, our 65 to 70 decibel gain on a particular region of the sky is an extraordinarily big challenge because satellites are now crisscrossing the sky and occasionally coming close to bore sight. Next slide, please. So here's an example of what happens when a satellite comes close to bore sight. Here's a satellite back in 2023 that came very, very close to our main beam. And you can see over on the left, that's basically the beam pattern for the Green Bank telescope on the sky, showing basically plus or minus 1 degree on the sky. And there's this NGSO satellite moving, and each of those dots are 1 second timestamps. So they move very quickly, right? And they are not close to bore sight for long, but when they are in that peak. Over on the right is just a slice through the gain of the GBT. You can see that the gain is something of order 50 or 60 decibels from out of the side lobes to when you cross close to the main beam. Next slide. So we've proposed some mitigations and initiatives, and the big one that I just want to mention briefly, and I'm going to try very hard to stick to 10 minutes here, I think I'll make it, is ODS, Operational Data Sharing. And what is shown in this image is that, the sort of traditional way you might think to avoid satellite space-to-ground transmissions is say, please don't point at us. And that helps. That's what we call zone avoidance. And we actually do have small zones of avoidance that we have reduced in size remarkably over the past couple of years. In fact, the initial zone of avoidance in New Mexico was New Mexico. And now the zone of avoidance in New Mexico contains the sort of the VLA antennas and also the Pytown VLBA antenna, and a smaller region around the telescopes in Virginia, West Virginia, and the Sugar Grove Research Station. Next slide, please. So how does this work? It's a two-way communication, and we have been testing this with SpaceX. We are also in discussion with AST Space Mobile and Kuiper, so we are having good discussions. It's a good sign that I know Jennifer and have talked to her on many occasions. And I think, one of the necessary things that we really have to do is stay in communication with one another so that we are aware of one another's needs and capabilities and limitations. So what we do with ODS is we share the near real time of our telescope observing frequency, bandwidth, and pointing. This is on an authenticated tokenized server that SpaceX reads data from right now. I say SpaceX because that's who we're currently actively working with, but this is an open collaboration. And what they do in real time is they respond to those data. So when they have a satellite that comes close to bore sight, they take one of two actions. If they are in what's called outer bore sight, which is not directly on bore sight, they can steer their phased array beams as far away from sites as possible. And when they get very close to bore sight, which we call inner bore sight, they can actually quiet their electronics. And this is all described in a series of papers that have been published. So this is all public information. On the right is the signal size in 1 megahertz bands crossing the 1990 to 1995 downlink band. This is the direct-to-cell downlink band that is utilized by SpaceX and T-Mobile. And what this shows is that the dotted black line shows the satellite position distance to bore sight. So you can see the scale on the right. It gets very close to bore sight right here at the peak. And as you go, you can see that there is some sort of signal there, but there's this one big signal as the satellite is getting very close to bore sight in the downlink band. The signal is getting quite strong, and then it drops to zero for that inner bore sight, and then it pops back up as the satellite comes back out. So we have tested this at the VLA and with the VLA and the VLBA, and actually this image down on the lower right shows channels 1 through 5. So the upper one is direct to cell in our L band. This lower one is actually Starlink signals, channels 1 through 5, the lower 5 channels. in the X band for us. Next slide. And what this shows is the remarkably large number of times that SpaceX actually takes action. And so this is basically the months of August and September. So some of the most recent data we have. On the left are the X-band inner and outer telescope boresight avoidance maneuvers. And on the right are the Starlink direct-to-cell, that's in X-band. And you can see when we're not operating in X-band, like around October 10th, when we don't have a lot of observations, the number of maneuvers is small. But then there are days where there are hundreds, if not thousands, of these maneuvers per day. And so it is an active system. And by the way, this is coming from VLA data. Next slide. I want to show you this. This is almost the last one. This is from a student project this summer. Actually, Blake Hutchison worked on these data as part of our program. And he made this great plot. It's a bit complex, but I think I can explain it pretty quickly. So this is showing system temperature in 63 gigahertz bands. So the bands are the colors over here. And the large letters at the top are the array configuration of the VLA. So it went from B configuration to A to D to C to B. So the A configuration is the largest, where the telescopes are up to 35 kilometers apart. D configuration is the smallest, where they're all located in a very small area. And so what this shows is the variation in system temperature as a function of time, starting back in 2023 and actually going through this summer. The black dotted line or dashed line is actually the number of direct-to-cell satellites that had been launched as a function of time by SpaceX. And then this dotted line, the right dashed line that's labeled ODS, is when we turned on operational data sharing at the VLA. And so what this shows us is that while we were starting to see, and by the way, the black part of the histogram is the downlink, is the 63 gigahertz that contains the direct-to-cell downlink channel. What we see is that when we activated direct-to-cell back in January of 2025, we actually had a fairly significant drop, and it looks like ODS was quite effective in reducing the system temperature in that downlink band for one of our telescopes. Next slide, please. So we have some challenges coming up. We are in the process of generalizing the use of ODS to our other telescopes. Green Bank presents some of the biggest challenges because of how observers use the telescope, but we're making progress. Hat Creek Observatory, Haystack, and DSA 2000, which is just starting construction, all have active ODS servers and have adopted our data format. All other satellite constellations, as I said, we are in discussion with several major satellite constellations about the capability to exchange information through this ODS server. But one big challenge that remains that I think this group would be well aware of is that there are the intentional emissions, and then of course there's the unintended emissions that come off of these platforms. And those discussions are very important and continuing. Both at ITU and elsewhere. All right, I think that's my last slide. Sorry, I went a little over. Thank you. Oh, good. Blake is there. I just got a note. Blake's there. Hey, Blake.
That's good. Thank you very much. I think we need to move a little faster now, but the excellent presentation. You're implying that the dynamic, some form of dynamic sharing, having the information about your observations and the lines you're observing with the satellite constellations is helping. The big question will come up is, how those techniques could work at the frequency bands this particular NPRM is talking about. But in view of the time, we move to Jennifer, and let's hear from a mobile satellite company perspective what the challenges are, particularly, if any, in the higher frequency bands. But Jennifer, floor is yours.
Sure thing. Thank you so much. I'm here in Geneva at the ITU, so we're actually dealing with some of these issues real time while I'm here, which is, Beau, if you could figure out a way to speed up the process, I'll buy you a bottle of champagne. So go to the next slide. Two things I just want to start with, though, before I go into my presentation, and talk a little bit about who AST is and about the spectrum abundance proceeding and some of what we're doing is first off, everyone is really lucky to have Veena here. Veena is a role model for many of us at the ITU and really led the way on a number of important issues, not just as chair of work 2003, God, I got the date wrong, but just as a leader in the radio spectrum regulatory arena. And so with that, two starting points. Two things I never thought I would be saying. One, that the FCC releases a proceeding with the word satellite and spectrum abundance in the same sentence. For those of you who've been around for a while, satellite has not always been seen quite in the same light that I think we're seeing with this administration. That's very positive from the industry perspective. And two is the change I've seen in the radio astronomers. So Chris, not just yourself and your colleagues, but I'd say the whole ability. I've been in the satellite industry, give or take 30 years, both at the FCC and private industry, and most recently at NTIA before I came to AST. And the radio astronomers have traditionally been very difficult to work with. And I'd say from what I'm hearing from my colleagues at other industries and what we've seen in our own company, it really is a changed relationship, and we really do appreciate the partnership we have, and we do recognize how important not just radio astronomy, we also care about Earth exploration and remote sensing and all that stuff, but we do have a formalized arrangement with the National Science Foundation and also with NASA. So I just want to say there's a real change, I'd say, overall, and I think that's irrespective of administration. I think the radio astronomers have become really open to working to find solutions, and we appreciate that. So AST Space Mobile, who are we? I've been with the company only since May. As I said, I came from the Department of Commerce, NTIA, and I can answer Beau's questions. Sometimes commerce doesn't always work perfectly together, but we try. But we are the first space-based cellular broadband network. So you'll see in the picture, we have really large antennas, but they're sustainable, and we're working very closely with the scientific community to make sure that we don't negatively impact whether it's radio astronomy, optical, and other important uses. But there's a reason we need these really large antennas, and we'll talk about that a little bit. But we need to get great reuse. We're not just bringing texting. Many of the services, if you look at Globalstar, Apple's product today, it's an SMS one-way product. If you look at SpaceX, it's two-way SMS. We've actually tested and are in the process of deploying our network, which will provide broadband directly to your device, to your unmodified device. I have the biggest cell phone in the world, so this isn't a great ad for it, but it can be any size. And so we've been working very closely with the MNOs. We're using two types of spectrum, both cellular spectrum and also MSS spectrum. But we're primarily using the service link. Our service links are all below 2.5 gigahertz. So when I talk about the spectrum abundance proceeding in a little bit, I'll talk to you about what we're doing and using it for feeder links. So with that, next slide. So just one of the things that I was excited about the company and what our founder and CEO is, he wants to really get everyone connected, and not just connected with voice or low speed data, but with broadband. And there are still a substantial number of people, and anyone who spends any time at the ITU will hear this from other delegates, who do not have access to broadband. So one of the things we're doing in places like Africa is not only connecting our satellites to 5G and 4G phones and beyond, but also to 2G phones. And of course, this is incredibly important for public safety. We've partnered with FirstNet in the United States and have an application pending at the FCC to work with them using their spectrum to bring broadband direct to FirstNet responders' devices. Next slide. So we talked about, I'm not going to lie, it's a really big antenna, and this isn't even our really big one. This was one that's up. We're actually, you'll see the next generation. The one you're seeing is the 693 square foot antenna. We're going to a 2,400 square foot antenna, which will start launching this year. It's a big antenna. But as I said, it brings a lot of benefits. If you look at it, and one of the things I found so amazing when I went to the factory, it's only about this thick. It's a little thicker. You'll see the hole in the middle where the functions of the satellite go, but it's a really unique satellite and has things like able to control beam forming within, so we can avoid country borders, we can avoid sites. Chris talked about radio astronomy sites, so we're able to design our network in a way where we can avoid interference or harmful interference into critical facilities that the scientific community may be using, or if we're using spectrum, making sure we're not going into other countries or interfering with other users. So with that, the next slide. And this is kind of our responsibility. So I talked already about some of the organizations we're coordinating with and collaborating, NSF, NASA. I'd be remiss if I didn't talk about the International Astronomical Union and their dark and quiet skies. And then also regulators. Of course, we're complying with the orbital debris requirements of the FCC, and we'll meet other orbital debris requirements should we start working with other governments. Today, our satellites are all US flagged. And here's just a few things we're doing. For astronomy protection, we're looking at specialized coatings, dynamic orientation. We're at a very low altitude, which helps, and precision orbital data sharing, which we think is very important. In terms of spectrum, my background, we're very efficient. Precision beamforming, I talked to you. We're putting our gateways in strategic locations, and then we're working to mitigate interference with the amateur radio users. And of course, collision avoidance is important. And then on our environmental footprint, our satellites fully burn up on re-entry. Next slide, please. So just a few milestones. I'd really focus on, I think the exciting ones were with Blue Walker 3, we did the first things, which were phone calls and public safety tests, which are terribly important. But Bluebird 1 and 5, just this past year, we had our first video call, and we've also done some streaming most recently in July. So next slide. This just summarized what I said, and since we're tight on time, I will move on to I think it's the FCC parts. Okay, so where are we? So probably the most important thing I can share with you is today we actually have our application pending at the FCC for our full 248 network satellite system. While we will be using other bands, we're starting in partnership with AT&T, Verizon, and FirstNet. And so you'll see, as I mentioned, these are all what we call low band frequencies. They're below 1 gigahertz. But if you look at our feeder links, you'll notice that they're in the Q and V band. So they're above 37.5. And that's where the spectrum abundance proceeding is really important. When we were looking to design our system, ideally, we would have used feeder links in KU, which is around 12 gigahertz, or KA band, which is around 28 gigahertz, but they're incredibly crowded today. So we were moving up into the QV band. And even with these bands are not all available in every country. So part of what the spectrum abundance proceeding is enabling us, assuming it moves forward and goes to an order, hopefully will allow us access to additional frequencies. And then I just put in our TT&C frequencies for information. So next slide. So I'd say, and I think Beau talked a lot about this, so really the importance of the FCC as a global leader on supporting the commercial satellite industry. If you look around the world, we're really out in front, in my view, not just because I'm a former FCC employee, but I do think the FCC is very focused on ensuring our leadership. And I wanted to give another example besides for this proceeding. The FCC was the first regulator globally to adopt the supplementary coverage in space order, which allows us to use terrestrial spectrum on a non-harmful interference basis. And I would note that they've actually noticed for this open meeting this month on the 28th, whether it will happen with the government closed, I don't know, but a really exciting notice of proposed rulemaking where they're proposing to streamline satellite licensing quite significantly. So that's something we're looking forward. So the spectrum abundance proceeding was really early on in Chairman Carr's tenure, where they really came out very early in terms of support for the commercial industry. In the bands we've talked about 12.2 to over 100 gigahertz. As I talked about, we've been very focused on feeder lengths. Veena went over these bands before, 42 to 42.5, 51.4 to 52.4. One of the important things which we've supported is protecting users in adjacent bands. And we think that's incredibly important, including for the EESS as well as for radio astronomy. I think overall, one of Veena's questions, I think when we were preparing is how did we see the record in the proceeding? I think overall, not just on these issues, there was a lot of support. I think more of the support from the industry came to the lower bands. I do think there's still some technical work that needs to be done to really make satellite service, of a certain quality and getting equipment and so forth in the higher bands. But I think that is something that's coming, and I think it's really important that our regulators are having foresight in the US and then elsewhere looking at those bands, because we're always going to need more spectrum, whatever the service is. So I think it's great getting out there in advance. So hopefully, Veena, I kept it under 10 minutes.
Very good, and very good comments towards the end, Jennifer, about the importance of this proceeding, and FCC or the US leading in there. Our last speaker, and I do want to keep at least 5-7 minutes for quick Q&A. Happens all the time. I don't want to shortchange the last speaker very much. So Luca, it's your floor, and please, you're the only one who will talk about the non-science services, the commercial services. So look forward to your presentation and how those services affect these, in these bands in the NPRM. Thank you. Go ahead.
Thanks. Thank you very much. So first of all, thanks a lot for the opportunity to talk. And I'll preface that I'm not a spectrum expert. I come more from the industry and sort of like technical system architecture domain, although I've worked a lot with the regulator teams and commercial satellite operators, and I worked in 3GPP for specifying new spectrum bands in RAN 4 and other areas. So my presentation is, promise I'm going to be very quick, and I'm going to be focusing on something slightly different, which is basically we are a technology company. And so our main interest is basically providing the tools, the technology tools to basically commercial and public sector entities alike to basically more efficiently manage and better manage the satellite networks on one hand, but also potentially address some of the issues that we discussed today. So if you can go to the next slide. Brief background about Aalyria. So we are a spin-off from Google Project X. We took two technologies from Project X, software platform for control and orchestration, which is going to be the main focus today, and technologies for atmospheric laser communications into a sort of like independent company. Next. And these two technologies are space-time and tight beam. Our main focus is going to be on space-time today. Next, please. So you can think of space-time as sort of like a network operating system for aerospace networks and satellite constellations. It's unique in its design in the sense that it was built from the ground up to be able to manage the dynamic nature of aerospace networks from the physics. So basically modeling the physical world, including interactions of those networks and wireless links with the physical world. And you will see this becomes important when you deal with spectrum, with spectrum emissions and satellite networks, terrestrial networks, interaction between satellite networks and other networks and other users of spectrum resources, for example, like Earth observation or like radio astronomy or Earth sensing or space sensing. And basically what our platform is designed to do is designed to be able to model any type of entity that interacts with that either is part of the network or interacts with the network, or that the network interacts with, and is able to essentially predictively understand the evolution of these entities and their motions in space and time and how they interact with one another. And it uses this sort of information, this knowledge about the network, as well as data feeds that it gets, like real-time weather, potentially any type of external data feeds, for example, even like external information from other providers or users of a resource, to then build a predictive capability that enables operators to efficiently manage their network from a control plane perspective and maximize the capacity efficiency with resource management and so on. If you go next slide. So I'll be very brief on this. The heritage of this technology comes from Google Project X, some of Google Project X initiatives in the wireless communication domain. One of them was Project Loon, which was a high altitude platform constellation for LTE direct-to-cell. Next slide, please. And really, the heritage that we have is sort of like being able to build and manage those direct-to-cell networks, including also deploying with PLMN, MNO PLMNs and MNO spectrum, and interacting also in terms of like operating within an environment where there are other users of the spectrum, also for backup. To give you some background, the Loon constellation used the E-band links for the balloon-to-balloon and feeder links, which you can see on the left-hand side. And these links were dynamically managed by our platform, Spacetime. So basically, in some areas, so the E-band is sort of like, you know it better than me, sort of like in some places unlicensed, in some places lightly licensed, in some places licensed spectrum band. And the Loon HAPs were moving across the world to provide service. And some of the backhaul links were actually spanning multiple countries where multiple regulations were in force. So what the Loon team had to build in the Spacetime platform from the get-go was a dynamic mechanism to even understand the local regulations, model them, in some cases even send liaisons to the regulators about incoming use of the spectrum. And then we would basically build those dynamic links by allocating the frequency channels and the power, for example, modeling the antenna side lobes and radiation patterns in a way that would be compliant with regulation and would also be protective of the other users of the spectrum. And this extended also, of course, to the direct-to-cell IMT spectrum that we deployed on, because, of course, we were sort of like dynamically leasing spectrum from MNOs to which we are providing essentially an extension of. But you can see like the heritage is very much in this domain. And if you go to the next slide. Yeah. So where we take the Spacetime platform today from that past heritage is basically providing primarily commercial satellite operators, but also other entities, for example, users of connectivity, or in some cases even government and public safety, or like in general public sector entities, with tools to for operators efficiently manage their constellations or other networks, including anything that ranges from the radio resource management and mobility management. So we model individual beam pointing, for example, like Chris was mentioning in the sort of like operational data sharing, that they share information about, for example, antenna pointing, the frequencies that they're listening on, and sort of like what their operational envelope is. Spacetime is essentially designed to model that information both from its internal digital twin, but also taking it from external sources, and use this information to inform the real-time operation and optimization of the constellation. And this really makes some capabilities possible that would otherwise not be possible manually, and potentially could open up solutions for operators to comply and to better work against basically meeting all the regulatory requirements and protecting other users. If you go to the next slide. So this is just a brief overview of what our system looks like from a visual standpoint. You can go to the next slide. It's just similarly for managing LEO constellations with beam hopping. Next slide, please. The part that I actually wanted to talk about a bit, and I apologize because it looks like in the PDF the fonts didn't quite look right, so there's some weird formatting issues. I will try to see if we can fix them later. So Aalyria some time ago started working on a concept and published essentially an API called federation. And more recently, as we deal more and more with basically terrestrial, non-terrestrial networks direct to cell, we've been thinking about, okay, how do we apply this concept of federation? So basically to help interworking between, in this case, between terrestrial networks and non-terrestrial network operators. But what we found is that this framework, this federation framework, can actually apply to a number of different use cases. If you go to the next slide. So I'll make an example based on the TN-NTN integration, which is a hot topic today. What are the main drivers from the commercial industry, or some of the main drivers? So first of all, it's clearly delineating it with some exceptions that TN and NTN networks, so terrestrial and non-terrestrial networks, will be operated by separate operators. So MNOs on one side, satellite operators on the other side. The model is often that MNOs seek to extend their coverage with the non-terrestrial networks, direct-to-cell, supplementary coverage networks via partner SNOs, and they want to provide essentially a seamless experience for users, including mobility. SNOs, on the other hand, that are building, for example, NTN direct-to-cell services, leverage those strong and want those strong MNO partnerships because this is part of their sort of like a business model and their channel sales, and this is a fundamental part of the ecosystem. There is also interest, for example, for government and public safety entities on things like disaster coverage provisioning. So let's say you have an outage in the terrestrial network, the satellite network can actually be a very efficient and means for providing resiliency, but you need a mechanism to do it reactively and quickly. And then the other factors which we talked about, which are the spectrum drivers. So like spectrum is a finite resource and in some cases a sovereign resource by the countries. But I think as Beau mentioned earlier, it's also a common good. Essentially, it's a common resource that is often used by users that are looking at the public sector.
So Luca, I have a hard stop in 1 minute. So if you don't mind wrapping up.
Yeah. So basically, in a nutshell, whether you're using dedicated spectrum or IMT spectrum, and there's always other situations in which the spectrum needs to be used. So what we're seeking to enable, if you go to the next slide, is with next again. Yes. So basically, what we're seeking to enable is essentially we've published a set of open source APIs that are now under public governance. That are designed exactly to do this, to implement this concept of federation between networks, and endpoints between those for federation can actually be several and different. Can be commercial networks, government services providers and users, but they can also be, for example, other users of resources like spectrum, for example, radio astronomy, to facilitate, for example, a secure means of doing operational data sharing and so on. And this can open up a number of new business cases, and it can also help making spectrum use more sustainable. Last point, if you can go to the next slide. Specifically in terms of like the TN-NTN, this is a bit technical, but basically what we're proposing is an open framework to provide an API for interworking between terrestrial and non-terrestrial networks for direct-to-device, direct-to-cell, which will include a number of functionalities related to spectrum management as well. When it comes to the frequency bands that we looked at, these are very high frequency bands that are used a lot by feeder links, as Jennifer also pointed out. And the ability to be able to model these transmitters and receivers and different uses of the spectrum in a time and space dynamic dimension, we think is going to be a fun, and most of all, to have an open set of interoperability and sort of like communication means or federation means between users, we think will be a fundamental tool in the toolbox to solve some of the challenges that we discussed about today. So
yeah. Thank you so much. And at least I wasn't aware of your tools, and I'm hoping that the TN-NTN is not just for the NTN system, the integrating with TN for the seamless connectivity, but if the application of these tools in actually addressing some of the interference situations with the terrestrial networks, interfering. So I think with such good information presented here, there's not a heck of a lot of time here for the questions, but I would still go to the audience. We already have a question for Jennifer, so if you can take that question, Jennifer. in the chat is why are you applying for 248 satellites when you indicated that you only needed 90 to provide the full coverage? So very briefly.
We actually said sorry, I missed that. So thanks for the question. So 96 satellites is what we've actually said for full coverage, just to clarify that. But the 248 will allow us flexibility, both in terms of bringing additional capacity. That's 96. If we're successful, you have to add capacity, and they're very large satellites with very high capacity. But also, I would also add, we are looking at using some of them for different frequency bands. So it really gives us the flexibility to deploy a network that's fulsome, robust, reliable, gives the sort of capacity for the demand that we expect to have, which 96 satellites will not be enough to meet the demand that we expect is out there for direct-to-device services.
Good.
Thank
I know I'm over time, but I would still like, if there are any questions from the audience to the panelists. We have covered so much material, more from the passive services perspective, because these bands are already there. FTC has noted in their NPRM that the bands are already allocated, whether they are FSS will go to coexist with them or go in the adjacent bands. So there are a lot of challenges to work with these bands to introduce the commercial services. We haven't really talked much about other than AST commercial services here, and the tools Aalyria is talking about, which are very good. If I really want to get optimistic, the tools what you are producing and the tools NRAO have come up, they should all go towards facilitating the sharing. Yes, go ahead. We have Emily, can you give the floor to the
Al? Thank you for your presentations, everyone. My name is Maria Geleva from University at Albany. So my question relates to the target sort of constituency for these satellite deployments, which in large part is to bring connectivity to unserved and underserved areas. And so taking in consideration that affordability tends to be a huge problem with bridging those connectivity gaps, I was curious, is there sort of what's the potential of satellite-based technologies to actually meet the affordability gap? And maybe as an academic community, is there anything that we can be looking at to help while keeping those other important services alive?
Jennifer, you want to address that, or do you want me to make just some quick comments on the affordability? Because
I think you are seeing dramatic well, first off, go Great Danes, fellow alumni. Glad to see you there. But I do think you're seeing tremendous decreases in costs in satellite technology and what's available today, and I think that will continue to go down. And one of the things I did talk to you was about making the service available on 2G phones as well, not just 5G. If you go to a place like Madagascar, where I've had the honor to visit, almost everyone has a 2G phone, but they don't always have coverage. So I think you will see different plans and different approaches, but give it time. We've already seen on the broadband side, I believe SpaceX's service, from a home broadband has come down dramatically. So Veena, I'll turn over to you for maybe some more comments.
No, it's a good challenge, and there are things happening on the parallel tracks to reduce the cost of the devices which people can make, and the more research we do, and if we can bring the cost of the handsets, the smartphones with the broadband access to $20-30, that's fine. But the affordability is not the only issue. To connect the unconnected, we have many other issues in terms of the digital skill set and people not adopting it anyway because of the safety and security. So I can go on that topic, separately. There are a number of issues. But yeah, a good point. And the more research one can do to reduce the cost, wonderful. Al, I'm sorry you had asked for the floor and I called for you, but maybe you didn't hear. Please go ahead.
Oh, thank you very much. Question for Jennifer. I'm wondering if you can share any details on how you might be able to coexist with passive EESS in the lower 50 gigahertz range. This is a very unique range for measurement of weather, and in particular, weather for many, many applications, not only, of course, for disaster management, general forecasting, but for global defense as well.
Thank you for the question. I'm a lawyer, not an engineer, so I will put my email in the chat, Al, and then if you email me, I'll get you in touch with someone. I'm just not the right person to answer that. I apologize.
Oh, I understand too, and I very much appreciate that. And we'll try to connect. Thank you.
Yeah. And Al, also, I think some of the techniques, 51 gig is a challenge. Of course, the next door, you have primary allocations here. So NFSS is happening in the 51 gig. Okay, there are no technology challenges or commercial issues there. So certainly we need either the tools, NRAO was mentioning the approaches, not the tools, but the approaches to mitigate the interference. And if there are other tools we can use, but that adjacent band coexistence will be required. And I think we need to figure out ways, and that's where we need the engagement of SpectrumX to figure out how we can reduce the out-of-band emissions, unwanted emissions from the satellite guys. It's an uplink band, and hopefully these are gateways, and there could be even location.
Yeah, it's important to note that really the entire spectrum from 50 to 58 gigahertz is important for weather forecasting and unique. In spite of the fact that not all of it has been allocated, even going back to Work 79.
Yes. Yes.
Well, and let me jump in here, Veena and Al. So we're going to have to wrap things up here, in part because, and also to just sort of advertise, SpectrumX is in the process of formulating a pretty robust, what we call flagship project around this issue. And we have to get out of the room to go take a tour of a facility here, a distinct facility here at the University of Wisconsin-Madison.
Wow.
And so we are really excited. I think you've set the stage with this panel for some great conversations as we conduct this tour and continue to flesh out our flagship project. And we would definitely look forward to following up with all of you to get your feedback on that project as it continues to evolve.
Thanks, Nick. And
let me take the opportunity to ask the audience to thank our panel. Hopefully you can hear the clapping. We're all very appreciative.